Okay. Good afternoon. Welcome to day 3 of the press briefings at the 46th DPS meeting here in Tucson. My name is Dr. Vishnu Reddy. I'm the press officer for the DPS. Today we have a very exciting program which includes asteroids and the planet Uranus. First, to my far right, I have Dr. Alan Harris, who's a senior scientist at MoreData. He's going to talk about population of small NEAs. Next, we have Brother Guy Consolmagno from the Vatican Observatory, and he's going to tell us why Vesta is not an intact protoplanet. Then we have Dr. Dante Lauretta, who's a professor at the University of Arizona, and he's also the principal investigator of the OSIRIS-REx mission, and he's going to talk about the target of the OSIRIS-REx mission, which is near-Earth asteroid Bennu. Then we have Dr. Imke, who's a professor at the University of California, Berkeley, and she's going to talk about some unusual activities that have been observed on the atmosphere of Uranus this year. And finally, we have Dr. Erich Karkoschka from the University of Arizona, and he's going to talk about the atmosphere of Uranus and what has been gleaned from the Voyager flyby, looking at some of the older archive data. Without further ado, I'll take over.
I'm all set. Yep. What do I do here? Oh, just move it that way. Okay. Just to be sure we get to the point before I run out of time, here are the 3 points that I want to make. I seem to be sort of the go-to guy for NASA to estimate how their surveys are doing to find near-Earth asteroids. And so every 2 years I do a reevaluation or re-estimation of the population. And I just completed one of those just a couple months ago, and I'll be reporting tomorrow on the result of that. Now, the first thing that they're highly interested in, NASA is interested in, is how they're doing with regard to these large objects, greater than 1 kilometer. We've discovered about 90% of them. My population estimate, just coming out now, is about 990, which is almost indistinguishably different from the last couple that I've done. An important result that came out of my latest analysis, though, is the small NEAs, the ones 20 meters or so in size, which NASA has gotten rather interested in, and also the Chelyabinsk impactor brought to light. My previous estimate was about a factor of 4 or 5 lower than bolide estimates had been. My newest estimate now comes pretty well into agreement, so I think Peter Brown and I are now good friends again. The last item is the so-called ARM mission that NASA's gotten infatuated with, and I put in a special estimate of the population of those objects. And I'll come over each of those points rather quickly. To track the progress of the Space Guard survey, so-called, I use a computer model which estimates the redetection rate of bodies as you go to smaller and smaller bodies, which fraction in the last 2 years are redetections and which ones are fresh discoveries. And based on that, we're able to estimate what the total real population is. And my previous updates have been falling further and further discordant with what seemed to be from the bolide data. So I did an updated survey model. I extended it to 20 years computer simulation rather than 10, since that's about how long it's been going on now. And I allowed for a variable performance because the surveys have been getting better and better over that 20 years. They're now reaching about 2 magnitudes fainter. And so when I did that, I came up with this population here that you see. And as I said, at the right-hand side of that, there's almost no change. The red line at the bottom is the total number of actual discovered objects, and you can see the blue line, or the blue dots there, is the estimated population, which of course diverges as you go to smaller and smaller, smaller fraction. And the latest model now comes right up to those colored symbols at the upper left, which represent the bolide detections, and the Chelyabinsk and Tunguska sizes are indicated on there. And you can see that the new model now is very, very close, and I'll come back to that in just a second. At that large end, There's just virtually no difference. This is every 2 years, my model estimates. The error bars keep getting smaller and smaller, and it's very satisfying. It's just necking down onto the same number, about 980, 990. The WISE satellite 3 years or so ago came up with exactly the same number, so I think we really do know how many things a kilometer and larger are out there. At the small end, there's just a blow up of that plot down at the small end, and in the size range from 30 meters on down, my previous estimate fell below that blue sloped line, dashed line. The current estimate is above it, and in particular, it's almost right on top of some of those ones that are based on infrasound data and bolide data and so forth that Peter Brown has collected together and published in Nature. So I think we're within a factor of less than 2, 1.5 or so, of the same size frequency distribution on that side. So that kind of lays to rest this controversy that came up when Chelyabinsk woke us up. Lastly, I just want to say a few words of this ARM targets. This is objects that are 10 meters or so in diameter, and their relative velocity to the Earth as they come flying by has to be less than about 2.5 kilometers a second. The average for all asteroids is about 25 or 22. And so they have to be very, very Earth-similar in their orbits. And I did a simulation of surveying to see how efficiently those are picked up. And the result, frankly, shocked me. I concluded that in the 10-meter size range, the current surveys we have, like the Catalina Sky Survey, are about 1,000 times more efficient at picking up those low-velocity things than the big ones, which means that currently, already, we've discovered about 1% of all of them that are out there, rather than 10 to the minus fifth or about 10 to the minus fifth completion for the general background of objects. So the number we've discovered so far is around 20. I'm guessing there's about 2,000 total out there. And of the word of caution, though, of the 20 that have been discovered so far that fit the criteria, 2 of those are certified rocket bodies. And we know how many of those are out there. We put them there. And there's about 100 that are at that size range, of which we found a couple. And I think that vindicates the estimate of about 1% completion. We've chanced to rediscover about 1% of the old rockets that we stuck up there. And so I think that really does kind of confirm that the total number of these potential targets are around 2,000. Well, good news is that 2,000 is plenty, you know, so we've got a lot more to find. Rich can stay employed for quite a while yet looking for these things. But the word of caution on this is that we need to be careful to characterize these things physically to be sure we don't come back with, would you say, an undesirable class of object that you go out to retrieve. And I'll just leave it there. Thanks.
Well, my story starts nearly 40 years ago when I was a graduate student here at the University of Arizona working with Mike Drake. And I was interested in asteroids and meteorites from asteroids. This is, of course, what we've learned from the Dawn mission. But what I was working on 40 years ago were these meteorites. The Howardites are mixtures of eucrites and diogenites. They're basaltic meteorites. Now, most meteorites are like the chondrites down at the bottom. They're the raw materials that we think the planets are made out of, or represent a good proportion of what the raw materials were. The basaltic meteorites are what happens when you take the raw material and melt it. The lava goes to the surface, and you can see that, for example, the aluminum in the basaltic meteorites is 10 times what the total aluminum abundance is. You could do the same thing with trace elements, which is what I did 40 years ago. That means if you started with 10 buckets of raw material and you melt it to concentrate the aluminum into the top bucket, the bucket that makes up the basalts, you've got to account for the other 9 buckets of stuff that is no longer basaltic. Mostly that's going to be olivine and metallic iron. Now, as it happens, the Dawn mission gave us a measure of the iron content in Vesta. Why are we excited about Vesta? Because we've got 1,500 of those basaltic meteorites. We don't have any of the meteorites that look like the olivine and iron underneath. So we assumed wherever these meteorites came from had to be intact. Vesta is intact, therefore they must come from Vesta. With that idea, we went to look at Vesta. We saw that Vesta, that red line shows you the range of densities and sizes that you could have for the metallic core, and the number, this is from a paper that was published this year by Erich and al., shows that the density of the rock above the core is around 3,000, 3 grams per cc. And so this is another one of their figures. They showed that you could have any range of crust sizes, but the one that fits using the densities we've measured at the Vatican for the Howardite meteorites and the densities we've measured for what we think that olivine center should look like, suggests that the crust has to be about 60 kilometers thick over that big core. Well, this is a problem. Dawn says you've got a really thick crust, at least 60 kilometers thick. There are 2 large impact basins at the bottom of Vesta, which probably excavated to 85 to 100 kilometers down. We've never seen any olivine. So the crust has got to be 60 to 80 kilometers thick to match the density, to match the fact we don't see an olivine mantle. But to make the Howardites, you could only have enough crust to make 10% of the mantle, which means the crust could only be 25 kilometers thick. In order to match the density, if you've got a big core and a thick crust, there's no room left for the olivine, so the olivine mantle must be small. But in order to make the HEDs, the olivine mantle had to be big. In order to match the gravity data of Vesta, the core had to be really big. But in order to match the chemistry of the mantle and cosmic abundances, the core has to be small. In other words, I can give you a model of Vesta that matches all the dawn data, or I can give you a body that can produce the HEDs, but it doesn't match the dawn data. So what's going on? We know that Vesta is covered in a great thickness of Howardites. We know Vesta today can't be that chondritic value because if the crust is too big, the core is too big. And so we've got to ask ourselves, where did the Howardites come from? How do we account for this mismatch? My real message is there is a mismatch and there is a problem, but I've got a suggested answer. What if the original HED parent body was actually a lot bigger than Vesta is today? So it's got the same size of iron core, the same amount of crust, and the mantle somehow went away. Well, how can you get rid of the stuff in between and save the stuff above and the stuff below? Mystery to me. It turns out Erich has done something called hit-and-run collisions that show that a body hitting a much bigger body, say the Vesta hitting something that looked like Mars, would be ripped apart and then reaccrete. The mantle would be squeezed out the size, the crustal stuff would fall on top of the core. Maybe this is a way that Vesta was made. Is this crazy? Well, we know the basaltic meteorites were made really early on. They were melted. The only way you melt them is by having aluminum-26 live inside them, which means the first million years or so of when bodies were being built. We know during that time that Jupiter was stirring things up and maybe even moving in this grand tack to completely stir up the original asteroid belt. And the original asteroid belt had 1,000 times more stuff in it than it does today. So there were a lot of these collisions. Why is this exciting? We went to Dawn. Dawn went to Vesta because the idea was that Vesta seems to be this intact protoplanet. Unlike all the other asteroids, it survived with the crust, mantle, and core. What I'm saying is it didn't survive. What we see today is a body that's been ripped apart and put back together. Again, it's unique. It's still only one of them that we've got. It's still a fascinating place, but it's fascinating for a reason different from what the Dawn team were expecting when they went there.
Okay, thank you for inviting me here today, and thanks for listening. I'm going to tell you about the target asteroid of the OSIRIS-REx asteroid sample return mission. It's asteroid 101955 Bennu, and we've wrapped up an extensive astronomical campaign which basically sets the scientific foundation that drives the hypotheses that we're testing with the mission. So just a quick overview of OSIRIS-REx and our science objectives, which are captured in the acronym that defines the mission name. First and foremost, we're an origins mission. We're going to what we believe to be a carbonaceous asteroid, hopefully rich in organic material and hydrated minerals that'll give us clues to the origin of life and the origin of water for our oceans, for example. We're interested in the spectroscopy. Through spectral interpretation, we look at the surfaces of asteroids and we try to infer their compositions, their grain sizes, their dielectric properties, and bringing a sample back will allow us to ground truth those astronomical observations, as I'll point out later on the presentation. We're going to an asteroid that has a relatively low delta V, kind of as Al alluded to earlier, and therefore represents potential resources of near-Earth space, particularly if it is a water-rich body. This is something that maybe you could process for life support or rocket fuel for furthering human exploration in space. And then because of the nature of its orbit, the fact that we can launch a spacecraft, rendezvous with the asteroid, and then return a capsule back to Earth means it's relatively easy for the asteroid itself to get back to the Earth. It represents an impact hazard. It has a relatively high impact probability late in the 22nd century, and we're interested in the Yarkovsky effect, which is basically the re-emission of thermal radiation acting as a small thruster that changes the orbit of the asteroid. And we would need to understand that force if we wanted to accurately predict whether or not this body was going to hit the Earth. And then finally, we're a regolith explorer. Regolith is the loose material that exists on the surface of these airless bodies, gravel-sized particles and smaller. We're going to document the regolith at our sampling site at scales down to the sub-centimeter, ultimately grab some of that regolith and bring it back to Earth for scientific analysis. Here's a quick overview of our mission timeline. We were selected for flight by NASA in May of 2011. We passed our preliminary design review and were confirmed by the agency in April of 2013. We're getting ready to begin full assembly, test, and launch operations, what we call the ATLO process, in February of next year, and we're working steadily towards our launch date in September of 2016. We've got about a 2-year cruise out to Bennu, so we'll get there in August of 2018. We spent about 2.5 years characterizing the asteroid, ultimately sending the spacecraft down for a 5-second touch and go to collect a sample. And then we have to wait for the departure window to open up, and that happens in March of 2021. It's a 2.5-year cruise home, so the samples are returned to Earth in 2023. And then we have an additional 2 years of support for curating the material and for analyzing the sample. So in preparation for that encounter and to help with mission design, we have performed an extensive astronomical campaign to characterize the target asteroid. Its orbit brings it close to the Earth every 6 years. It was discovered in 1999, and we got some radar Arecibo ranging data and Goldstone ranging data and imaging from Arecibo. And then it came back in 2005 and again in 2011, and we got ever more data as each of those apparitions occurred. And over here on the right just gives you an example of some of the facilities that we have used to characterize the asteroid, including the Arecibo radio telescope, the Hubble Space Telescope, Spitzer Space Telescope, Herschel Space Telescope, and a wide array of ground-based telescopes in Arizona and Chile and the Canary Islands and elsewhere around the world. So we have a great database of the asteroid. We understand it pretty much as well as you could any near-Earth object without sending a spacecraft to it. Over here is just a highlight of some of the radar data. You can see the raw data over there on the left, and then a reconstructed three-dimensional shape model over there on the right. Through processing of this data, along with some light curve information, we know a lot about Bennu. We know its size is averaging 492 meters in diameter. We know its shape, which has this fascinating spheroidal spinning top with a pronounced equatorial ridge, something that we see actually kind of common in the near-Earth object population, yet we've never sent a spacecraft to investigate something with this shape. And we know its rotation state. It's rotating every 4.3 hours, and it's got 180 degree obliquity, which means its south pole is basically pointing straight up, where you would expect the North Pole to be. It's what we call a retrograde rotator. We've also used radar to probe the near-surface bulk density because the wavelength goes in about 1 meter into the upper surface of the asteroid, and we've backed out a bulk density of about 1.7 grams per cubic centimeter in that part of the asteroid, and that gives us compelling evidence that we are, in fact, going to something akin to our carbonaceous chondrite meteorites, and therefore, hopefully, we'll achieve our science objectives. So we've done a lot of work to take all of that astronomical information and couple it with geochemical models of the solar system and dynamical models of how Bennu could be delivered from the main belt into the near-Earth object population. It's currently on an unstable orbit and will probably fall into the sun in about 10 million years or so. So it didn't originate in near-Earth space. It had to form out beyond Mars and then somehow get delivered into the inner solar system. And so here we've just put together a very abbreviated outline of our hypothesis. We know that Bennu most likely formed in the earliest stages of the solar system when we had a protoplanetary disk surrounding our protostar. That's where its primary chemistry and mineralogy was established. Because of the hydrated nature, we think it had some parent body processing, probably heating by aluminum-26, melting some primordial ice, and then driving hydrothermal evolution to create clay minerals and probably modify the organic constituents. And that was probably a body on the order of 100 kilometers across or so, so relatively large. That had to get shattered in a catastrophic disruption. We think that happened maybe 700 million to 2 billion years ago. And then Bennu itself reaccreted from fragments on the order of 100 meters and smaller into the object that we know today. It would have had an irregular shape after that reaccretion, and we think this phenomena called the Yorp effect, which is related to the Yarkovsky effect, but changes the rotation state of the asteroid, probably modified its shape. Basically, it started to spin it up, kind of like a windmill-like effect, and that drove material to the equator, forming that spheroidal shape and that equatorial ridge. Yarkovsky played a role because it's a retrograde rotator. Yarkovsky causes the semi-major axis to decrease, so it was moving inward in the solar system, probably hit the Nu 6 resonance that shapes the inner edge of the main asteroid belt, and that was the phenomena that sent it from the main belt on into the near-Earth object population. And since then, over the past couple million years, it's probably been doing a series of planetary encounters. We know it's come very close to the Earth over the past couple hundred years, probably did some close encounters with Venus, maybe with Mars, and those tidal forces that occur during those could also reshape the asteroid. So this is a hypothesized timeline that we've put together. And of course, this shapes basically the scientific foundation for the sample analysis plan. So we're going to take a very hypothesis-driven approach. We're going to use a wide variety of geochemical and cosmochemical techniques to see if we can test these theories when the sample is back on Earth in 2023. We've also done something very fun with this. We've created a movie. Here's a little bit of a preview for it. I'll be showing the entire video during my presentation on Friday morning. We don't have any sound. Oh, here it is. So this was produced by the Goddard Space Flight Center animation studio. There's OSIRIS-REx going in for the sample. So the preview will be on Friday morning, and then the entire video will be released to the public on November 18th. And then just to wrap up, the manuscript was just accepted and finalized for publication yesterday, so it is now available on the early view of Meteoritics and Planetary Science. And I just want to highlight that the work is dedicated to Mike Drake. This will be in the special issue of MAPS. Mike was the original principal investigator for OSIRIS-REx. He and I worked together for 7 years, writing proposal to win this mission, and then he passed away about 4 months after that May 2011 selection date. We have a wide variety of resources on the internet. If you want to learn more about OSIRIS-REx, I'll direct you to the links that are on here, and thank you for your attention.
So I'm excited to tell you about our most recent observations of the planet Uranus. But before I do that, I'd like to give you some background. So Uranus orbits the Sun in 84 years, and its rotational axis is within the ecliptic plane. So when the Voyager flew by in 1986, saw its south pole. The south pole was pointed towards the Sun at the time, and Voyager did not see very much, a pretty bland planet. Well, we'll wait for Erich's talk after mine. But only after stretching the images a lot, some faint cloud features could be detected. So while Uranus progressed on its orbit and the northern hemisphere came into view, in fact, Erich Karkoschka made images with the Hubble Space Telescope, and the latitudes that came into view for the first time after having been in the shadow for 40 years showed a lot of activity, a lot of cloud features at those high latitudes. Well, it was predicted that the storm activity, cloud activity, would reach a maximum near equinox in 2007, when the Sun would be directly overhead the equator. And indeed, with the Keck telescope, we did see a lot of cloud activity. Here are two images. The bottom one are taken at 2.2 micron, where the methane and hydrogen absorption is very strong, and so not much of the sunlight gets reflected back from the planet, since most of it is absorbed by the methane gas. The top images show images at 1.6 micron, where the methane absorption band is weaker, and therefore you probe a little bit deeper into the atmosphere. So we see these quite large features, and this was the first time in 2004 that a cloud feature actually was detected at 2.2 microns, so very high up in the atmosphere above the methane cloud layer. We further noticed that at that wavelength, at those high altitudes, the features sort of varied quite a lot, because 4 days later it had almost disappeared. These other features that you see here, if I can get the pointer, probably not. These are actually moons of Uranus, so they are not cloud features. So we observed Uranus since 2001 with the adaptive optic system on the Keck telescope, and this is a series of images through 2009 at 2.2 micron. And you can indeed see that there's just not much going on. The image at 2004 that I just described to you. In 2005, at the northern hemisphere, we see what at the time was the brightest feature ever seen on Uranus. So we had a big press release at that time as well. And then until this year, in August, when we pointed the telescope at Uranus, we saw a lot of cloud activity. And in particular, I want to focus your attention on this large cloud, which was also seen at 2 micron. And it consists of a number of little blobs in the clouds. And when you do a deep projection, you make a latitude-longitude map of the cloud feature and superpose images at different wavelengths. You can actually see that the clouds are at different levels in the atmosphere. The blue ones are deeper in the atmosphere, the red ones are higher up, but overall the entire cloud is pretty high up, above the 1 bar level, above the methane absorption, methane clouds. One day later, however, we were really surprised. We saw these images here where at both wavelengths, 1.6 and 2.2 micron, we saw incredibly bright cloud feature. And in particular, at 2.2 micron, we have never, ever seen anything like that, as you could have seen on the previous images. So making a longitude-latitude map of this one, we also see that the cloud consists of different components at different levels in the atmosphere, again, between about 300 and 700 millibar, pretty high up in the atmosphere. So at this point, we alerted the amateur community and said, gee, guys, just go out and see if you see something unusual in Uranus' atmosphere. So they went out, and indeed, they did see unusual activity. However, it's not the bright feature that we saw with the Keck telescope. It's that what is circled with a little green ring, a much fainter cloud feature, much deeper into the atmosphere. So to show you some of the amateur images of that cloud, here are some in blue from Anthony Wesley. We see an image with and without the cloud feature, and then there is one by Marc Dacroix and Collat, taken with the Pic du Midi 1 meter telescope, and here you can see that The cloud feature is brightest once it is at the center near the meridian, and it's fainter near the limb, which also tells us that it is deeper in the atmosphere. The Keck images showed us that that feature is at about a few bar level. So we then use these images to go out and trigger our target of opportunity Hubble Space Telescope proposal, which Cuneo was the first author, the PI, and fortuitously we got this really intriguing image where we saw both features. We saw the feature clearly seen by the amateurs at the visible wavelengths at the higher latitudes, and we saw what we think are the remnants of the very bright feature that we first saw with the Keck telescope. So the bottom line is there's a lot of dynamic activity in Uranus' atmosphere, and we have really no idea why, because this was definitely not predicted. The theories predicted that indeed it would just fade away and Uranus will be bland once again like during the Voyager era. So we're excited and we hope that the theorists will take this on and explain to us what's going on. Thank you.
Well, thank you for that nice introduction to Uranus. And I'm presenting results about the rotation of Uranus funded by NASA. And in a nutshell, we have observed the rotations of planets for 350 years, and everything seemed symmetric, quite well behaved. There was one region which we haven't observed because we couldn't see features. And so I investigated this region, I found features, I found the rotation, and it's defying our current understanding. What's unusual about this research is how old the data is. Usually discoveries like this one was 3 months old data, but my work was done with 28-year-old data, so 100 times as old. I looked through hundreds of those presentations here at the DPS, and I only find one that was from 1986. That was the Comet Halley investigation. So that's unusual. What I did, however, was I applied new image processing techniques to that data, and so I could see features that other people couldn't have seen. And one of the many techniques is I was stacking 1,600 images on top of each other to reduce the noise dramatically. So here, that's how the planets rotate. The white grids show the interior rotation, and then the color shows the atmospheric rotation. And in the beginning, the colors were aligned with longitude, but you can see some places where the planets rotate much faster than others. They get sheared apart. On Jupiter and Saturn, you see it at some specific latitudes, but Uranus and Neptune, it's really very strong shear, and that's important because that tells us a lot about the atmosphere and the planet. So the rotational measurements have been done a long time. 1665 was when Cassini measured the rotation of the Great Red Spot. In the last 350 years, lots of astronomers have worked on it, and they almost finished the job, but there was one spot in the solar system, the southern half of the southern hemisphere of Uranus, where we all failed. We took thousands of images with Voyager 2, with the Hubble Space Telescope, with ground-based telescopes. We took dozens of filters from the ultraviolet to the infrared, and we came up with nothing. Well, except there was one feature, Voyager's. So it was embarrassing. We took so much, and we didn't have any result. But today I revealed dozens of features where only one was known before, and they spread out over the whole region where we didn't know the rotation, and so now the mystery is solved. That's how Voyager saw Uranus, the planet, the interesting ring system, and 10 inner satellites. 9 of those satellites were discovered right when Voyager approached, and then one satellite, Perdita, in the upper right, that wasn't recognized for 13 years afterwards until I looked at the images and found it there. I can show you now Uranus like this, because with my image processing techniques, I can enhance it 300 times. And so it looks like an interesting planet. And to me, it felt like there's a new space mission to Uranus with fantastic images. And for a year, I was the only person in the world who was allowed to view them. But now I'm sharing it with you. So the theme of this talk is about the rotational asymmetry of giant planets' rotations. And on the vertical axis on the left, that's the latitude of the planet. On the bottom is the ratio of the rotational period between the north and south hemisphere with symmetric latitudes. And if you look, that ratio is between 0.99 and 1.01. So the rotational asymmetry is about 1% or so. And that may seem surprising because the difference in rotational rates varies about 10%, sometimes even 20 or 30%. So it really shows the planets are quite symmetric with the rotation. Everything is fine. For Uranus, the data was up to 45 degrees. And then above there, there's just that one little circle where we had data. So now I add my data, and it really doesn't look like anything what we have seen before. The data goes through that circle, so it's consistent with the previous data, but it's not consistent how we estimated it. The differences are about 50 meters per second, so that's about hurricane wind speed, so it's quite significant difference. And the accuracy of my data is about 100 times better, so the error bars are really smaller than the width of those lines. What's interesting is it was supposed to be smooth profile according to our current understanding, but I found many kinks here in that profile, and so we have to learn a little bit more about how Uranus does that. One interesting feature is between 58 and 68 degrees, where the rotational rate does not decrease towards the South Pole. Everywhere else it does, as we expect, but here it stays constant. That's a region in latitudinal extent about as large as the United States east-west extension. And so what if someone would tell you, well, the winds on Earth behave like they should be with low pressure and high pressure system, but all across the United States we have the same wind speed. So somehow the winds in the East Coast know what the winds do in the West Coast. You would say, that's crazy, how is that? But Uranus found a way to do it, and we have to figure it out. I don't know what it could be, but it's possible that there's some large structure in the interior which causes the rotation to be constrained this way. Maybe it's a big convection cell, maybe it's an anomaly in temperature or chemical composition. We just have to see. There is actually possible there's a similar feature in the northern hemisphere. Larry Stromovsky has worked on that observations, so maybe it's not unique. So in summary, if we could find out about the interior structure of Uranus with these observations, that would be great, because we almost have no data about the interior of the giant planets. NASA is sending the Juno spacecraft. They're arriving in 2 years. But this way, maybe we already have data now on Uranus. And because there are some 1,000 exoplanets of similar size, maybe that changes our view on the exoplanets. Treasures can hide in all data, and it doesn't matter if it's features in Uranus or satellites or anything else. The last point is the blandest region among the giant planets turns out now to be the dynamically most interesting region. And that's counterintuitive, because usually we chase what's interesting on the outside, and then we hope we find something interesting inside. But here, there's something interesting in the inside, and it was blanketed by something really bland, and nobody looked at it. And so for 28 years we could have found out, but nobody did. And so that's a delay of 28 years in those research results. Thank you.
Okay, thank you. We'll open up for questions.
You have a question over here?
Tom Beal from the Arizona Daily Star. Brother Guy, which came first, your reassessment of your graduate school work, or your topic for your lecture tomorrow?
Oddly enough, it was the topic for the lecture tomorrow. I didn't realize that I'd be giving my own example of what I was talking about, an idea that was almost correct.
Leslie Sage, Nature, for Imke.
Can you rule out impact origin for at least some of your features?
I don't think it'll be an impact origin. Certainly for the deeper cloud feature that stays together pretty well. We have seen that now with both the from the amateur images and the Hubble Space Telescope images. It is seen deeper in the atmosphere, and typically for impacts you see it much higher up. And so I don't think it is related to any impacts.
This is Rick Feinberg. I have from the AAS. I have a couple of questions. One for Al Harris. In your first diagram where you showed the new data matching the bolide data, the survey data matching the bolide data better, there was a red curve that was significantly below the blue curve. What is it going to take to push that red curve up?
You're talking about the red curve that ends at about 10 to the 4th or so?
Yes, that's right.
Yeah, that is the number, the cumulative number of currently discovered near-Earth asteroids, which is about 10,000 now, 11,000 something. And what it'll take to push that curve up? Well, just to keep surveying, keep hunting. That's just at the far left end of that curve is just exactly the cumulative number that have been discovered. But of course, if you go up to the total population at that size, we're talking 10 to the 9th objects, and so there's no way we're going to find the last 1 meter object. So that curve actually creeps up very, very slowly with the surveys. But what happens is that curve creeps up. The differential of that, in other words, in each size bin, we get more and more objects, so our statistical estimation of that total population that's clear up to 10 to the 8th to 10 to the 9th gets better and better and better. So it would be hopeless to find them all, but finding some tens of thousands of them really nails the statistics of the total.
Okay, here's a question from Alex Witza, who's writing for Nature. This question's for Erich. Can you walk us through the colored bands in your video that centers on the south pole of Uranus? What do the colors represent? So I think she's referring to the video that you showed of the planet rotating, the planets rotating.
Yeah, in the beginning of the movie, every longitude was colored in a certain way, and then because winds move east and west, they get sheared out. And some latitudes rotate faster than others, and so soon that you can see spirals on Uranus because the area around the South Pole rotates much faster than the equator.
So are the colors representing wind speeds?
The color represent a certain atmospheric particle, and in the beginning, all one longitude was colored with a certain color, but as the particles move away from each other, some move faster than the other one, the colors spread out.
Okay, so we're seeing different streams of material.
Exactly.
Getting spread out. Okay, great. And are there more questions inside? Okay.
Yeah, Tom Beal again from the Arizona Daily Star. Dante, there was exciting news this morning from Rosetta, and I wonder what happens there, how it will inform what you are doing, or at least buoy your spirits for that adventure.
Absolutely. The whole OSIRIS-REx team here in Tucson gathered in our auditorium to watch the ESA TV live feed of the Philae lander on Comet Churyumov-Gerasimenko. And there was certainly a period of time where they thought they would get the signal and there was no signal. So for me, I just flashed forward to the touch-and-go sampling event for OSIRIS-REx and imagining when that final success signal is going to come down and we can all take a deep breath and realize that it went well. We are very proud and excited for our European colleagues, and I want to acknowledge that they've been very cooperative. We have a great collaboration established with the Rosetta team and OSIRIS-REx. We face very similar challenges, accurately navigating a spacecraft in a microgravity environment around a small body. So we're learning a lot from their operations. And then sample site selection, they have to go through a down select after they get the global characterization of the target, where do they think the safest region on the comet is to put that lander down. So we'll work with them as they get through this process, and we'll have a briefing probably early next year how they went through that and what we could learn. And then finally, as I've been communicating to my team, they didn't expect that comet to look that complex and that scary from a landing perspective, from an operations perspective. And so I've made sure our team is aware of what they thought the comet was going to look like and what it really looked like. We have this great model of Bennu and what we think Bennu looks like, but get ready for the unknown, right? Every mission we've ever flown has surprised us. OSIRIS-REx will certainly uncover some new things, and we've got to be prepared to deal with those.
Okay. Leslie?
Leslie Sage from Nature for Al. I remember years ago talking to Erich and his view was that the main threat to Earth is coming from dead comets. And I wonder if, and it seems like the asteroid threat now is pretty well characterized. Have you tried to characterize the threat from comets?
Well, not exactly. Now you said dead comets. Are you referring to dark?
Yeah, dark comets.
Things that are not diffusing stuff, yeah. Gene Shoemaker many years ago hypothesized that there could be what he sometimes referred to as stealth asteroids or objects, near-Earth objects, that we couldn't find because they're simply too low albedo, and those would hypothetically be the ones that have quit outgassing comets that are very, very dark. I think the concept, the idea that there's a big stealth population out there was laid to rest by the Weiss mission, which more or less authenticated the distribution of albedos that we had assumed from the discovered objects. I mean, it's a little bit like looking under a lamppost, you draw a conclusion from what you see. And so optical surveys see the bright stuff, and so it was suggested that there could be this stealth population out there that we just really don't see. But I think the Weiss mission has now surveyed the near-Earth asteroid population well enough that that population doesn't really exist. Now, there is, of course, a population which is not necessarily dead objects, some of them quite active comets, that are, real comets. Periods of 100 years and longer and so on. Well, of course, we can't survey those, dead or alive, until they come close to the sun. And so there's a big population of those things, and they can just come screaming in someday and one on a collision course. We don't know that it wasn't a comet, in fact, that did in the dinosaurs. So when you get to the really big size, yeah, that's a substantial part or a significant part of the impact risk. But the truth of the matter is there's not much to be done about it because there's no real hope to find them more than a year or two or three in advance. Like Comet Hale-Bopp was really huge. It was only discovered a couple, 3 years before it arrived. And I was at JPL at the time, one of my JPL colleagues, Paul Chodas, did a simulation to estimate if it was on a collision course with the Earth, when would you know it? When would you be able to say, yep, it's going to hit? The answer to that was at most 3 months. I mean, we discovered it 2 years ahead, but the thing is spitting, and it's not completely Keplerian motion. It has non-gravitational forces, and you can't really certify that that's going to hit the Earth until about 2 or 3 months in advance. And what can you do then?
I have another question. This one's for Brother Guy. Have you discussed your new conclusions about Vesta with the Dawn team, and are they supportive of your conclusions, or are they pushing back?
I think they're horrified. I first presented this material at Asteroids, Comets, and Meteors in Finland in the summertime. And before I even got up to speak, the principal investigator of Dawn in his review said, and by the way, you're going to hear a talk claiming that it's not a protoplanet. Don't listen to him. But I think that when they understand what it is I'm saying, and the numbers are pretty simple. I'm not doing any kind of elaborate analysis. It's simple mass analysis, simple density. There's no place to hide the olivine. The olivine must have gone away. When you realize that, I think it really is the first exciting and totally unexpected result that comes from dawn. And I've been frustrated because all along, yes, everything was exactly what we expected. Well, if it was all expected, then why did we bother going? This is why we bothered going, because I think it is an exciting new result that if it turns out I'm wrong, it's going to be for interesting reasons. So either way, it's an exciting result.
And do you think that when Dawn gets to Ceres, that it might find something similar, or is Ceres sufficiently larger than Vesta that you really don't expect anything similar?
I honestly don't know at this point. The Vesta that I described is still smaller than Ceres. So we're talking about a population of bodies that we know are out there. But on the one hand, we shouldn't think we know nothing about Ceres. We've got 30 or 40 years of people who have observed it quite a wet. But we shouldn't think we know everything about it. And you should be willing to expect the unexpected, just as Dante was saying you have to do with any spacecraft mission to anybody.
Okay, with that, we'll conclude the press conference. Tomorrow we're having a seminar for science writers or journalists from the New Horizons team. They want to do a preview of what to expect next July when they do a flyby. So we'll have the team members up here, and the members of media can ask them questions about what they plan to do. All right, thank you.